All right, so we've got a few Rolle's theorem and mean value theorem problems to tackle today. So for these two problems, we're looking to see why Rolle's theorem does not apply. Remember that our requirement for Rolle's theorem is for our geez, why can't I just speak right now? Our function to be continuous and differentiable everywhere in the interval, and for the outputs to be equal. So let's check that the outputs are equal first. And these problems, I'm totally fine with the use of a graphing calculator to understand what's going on the interval. I'm about to sketch the function for mine on the interval -1 to 1. So mine looks like the graph of 1 over x, except because it is the graph of 1 over x, except the curve, the elbow that's normally in the third quadrant, is made positive by the absolute value. So it's now in the second quadrant. So the reason that Rolle's theorem doesn't apply here is because we have a vertical asymptote. Right? And that's inside my interval -1 to 1. So my theorem is, Rolle's theorem is not, the function is not differentiable everywhere. In the interval -1 to 1. So Rolle's doesn't apply. All right, so we have two things for Rolle's. One, our endpoints y values must be equal. And two, we must be differentiable everywhere. So maybe it'll be helpful if I remind you when we're not differentiable. So we're not differentiable if we have a cusp, a corner, a cusp, a vertical tangent line, or of course a removable discontinuity because we're undefined at that point, or a vertical asymptote. All right, so these are all cases where we're not differentiable. Okay, now let's go on to using Rolle's theorem. So for these, it's going to work out that everything's nice and pretty. We're differentiable on the interval, and our endpoints are equal, but let's prove it anyways. So our y values for our endpoints we get by subbing those points in. Each of them equals 0. We've got a quadratic function, all right, with 3 and 0 as our zeros, and it's a negative leading coefficient, so it opens down. Looks something like this, right? You can get a more accurate graph by looking at your graphing calculator or Desmos, but Rolle's theorem says that we have to have some point between 0 and 3 since the y values are equal where the derivative equals 0. So looking at that graph, we do see that there is some point where that's true. All right, and we also see that it's continuous and differentiable everywhere on that interval. So we've got these two are equal, which is good, and it's differentiable on the interval. I always feel like it takes forever to write differentiable, but maybe that's just me. So both of our conditions are met. So once we've got that, we can say that there has to be a value where the derivative equals 0. So let's find our derivative. Our derivative is going to be negative 2x plus 3. And we know that there has to be a spot where that equals 0 on our interval, so we solve it. So x equals 3/2. We substitute back into our equation to get the y value of the point. And when you do that, you will get 9/4. So our point is 3/2, 9/4. And that's that point where the slope is 0. So that's the point right here. All right. We're looking at this and we're saying why the mean value theorem doesn't apply on the interval 0 to 6. So if we're looking at 0 to 6, right, the mean value theorem would say that the average rate of change, the slope of the secant, must equal the instantaneous rate of change, or the slope of the tangent, somewhere on that interval. So we're going to figure out why this isn't true. And it's because we have two conditions. It must be differentiable everywhere on the interval. Right? And we also must be continuous everywhere on the interval. Right? Continuity, differentiability implies continuity. If it's differentiable everywhere, it's continuous everywhere, but the other way around isn't necessarily true. I say continuity because sometimes it's easier for people to think about continuity and then differentiability, right? But really, if we had the first condition, we would have the second one satisfied. So you'll notice we have a removable discontinuity here at x equals 2. So that means we're not differentiable. There's no tangent line that we can find at that hole, right? So we're not differentiable or continuous at x equals 2. Because we're not differentiable anywhere on the interval, the MVT can't apply. Right. And lastly, we're going to look at an application of the mean value theorem, as well as a bit of a blast from the past with a tangent line problem. So we're going to consider the graph of negative x squared plus 5. So that graph is going to have intercepts at plus or minus root 5. All right, so we're going to look at the interval -1, 4 and 2, 1. So we're looking at that specific piece of the graph here. If I can select a pen, geez Louise. So we're looking at this piece of the graph. All right, so we have to find the equation of our secant line. So for this, we're looking for our slope, which is going to be our average rate of change on the interval, -1 to 2. All right, so for that, So we're going to do f of b minus f of a over b minus a. In this case, b is 2, and a is 1, negative 1. And we're given our f's, so we've got 1 minus 4, negative 3 divided by 3, or negative 1. All right. Mean value theorem says that our derivative at some point c is equal to our average rate of change on that interval, as long as we're differentiable and continuous everywhere on that interval. We can use it. So we need to know what our derivative is. Our derivative of negative x squared plus 5 is negative 2x. So we set that equal to, well, that's negative 2c, equal to negative 1, and we solve, we get c equals 1/2. And then to find our y value, we plug the 1/2 into our equation. So I've got negative 1/4 plus 5, which is going to be 4.75, right? Or 19/4, I do believe. Yeah. And lastly, we have to find the tangent line that goes through C. So tangent line, our equation, f of x minus f of c, which is 1/2, equals our derivative at 1/2 times x minus c, x minus 1/2. We've got f of 1/2. We don't have f prime of 1/2, so we still need to find that. Our derivative, remember, was negative 2x, so I've got negative 2 times 1/2, or negative 1. So let's sub in. We've got f of x minus 19/4 equals negative 1 times x minus 1/2, negative x plus 1/2, and then we add the 19/4 to both sides. And when you do that, you will get 5.25 or 21/4. Whoopsie, I need my x in there, negative x plus 21/4. So that's our tangent line equation. So go ahead and give your You Do problems a try and message or ask me any questions you have. Adios.